Hi, this is Troy Tacey from Fordham University, and this is my second of a multi-part video presentation on the coronavirus outbreak. What we're going to be speaking about in this video is predicting whether we expect an epidemic to grow or shrink, how long we think it might last, and how this is going to depend on this thing called R, or the reproduction number that you might have heard about in the news or read about recently. So what we did previously in the first lecture is we learned how to write down a simple categorical model that describes an epidemic. We called the model an SIR model because it described how people in a population flow from being susceptible to being infective and then being recovered. So we refer to this model according to the acronym of those different states that people could be in. We call it the SIR model. After we wrote down this model, we dumped it into the equations for the model into Excel, and we were able to show that the simple SIR model is able to replicate the basic shape that we typically see from viral outbreaks such as influenza, and what we expect the coronavirus outbreak to look like as well. Now, the main focus of this video is going to be whether or not we think an epidemic will grow or shrink, and then defining this thing called the reproduction number. So from the previous lecture, we had this equation that described the number of infective people in the population. And what you will see in each of these different terms that's up within this equation is an I, and that I is either followed by a T or it's followed by a T plus 1. What I want you to think about is, suppose that this T represents today. So if I have IT, that represents the number of people that are currently infective in the population. So we have an IT here, we have an IT here, and we have an IT here. And what we're doing is we're using the right-hand side of this equation to predict how many people will be infective tomorrow. So this I has a T plus 1 on it. So we have today plus 1 day gives us tomorrow on the left-hand side. Now, how do we predict how many infections we will have tomorrow based on what we have today? Well, the first thing we're going to do is write down the current number of infections. Then our second term is the number of people that are our inflows from the susceptible state into the infective state. And as we saw in our last lecture, that's going to be equal to IT multiplied by the number of contacts, multiplied by the rate of transmission if a contact between a susceptible and an infected person occurs, and then finally multiplied by the number of susceptible people within the population. So this term here tells us how many people are going to flow from the susceptible group of the population into the infective group of the population. And then this last term is the number of current infective people multiplied by the rate of recovery, which is 1 over the average duration of the infection. So if we take our current number of infectives plus our new infectives minus the people that recover in the current period, we get the number of people that are infective tomorrow. Now, will the epidemic grow or shrink? Well, we can simply look at whether or not IT plus 1 is bigger than IT, or if IT plus 1 is smaller than IT. So if IT plus 1 is bigger than RT, obviously the epidemic is growing. Now, according to our equation up above, this only happens if C times D times S times D is a number bigger than 1. On the other hand, if IT plus 1 is less than IT, then our epidemic is getting smaller. We have fewer infective people tomorrow than we currently have today. Now again, if we look at our equation, this is only true if C times S times D is less than 1. So the answer to this question really depends on just the value of C times D times S times D. And this is an important enough number in epidemiology that this is referred to as the reproduction number, or sometimes it's just simply called R. Now intuitively, what does R tell us? So again, R is the contact rate multiplied by the transmission rate, multiplied by the duration of the infection, multiplied by S. Okay? So essentially, again, C is the number of contacts you have per day. The contacts with susceptible people in the population are the only ones that count. So we're multiplying C by the fraction of people in the population that are susceptible. And then of those contacts between susceptible people and infected people, the only ones of those that count are the ones that result in a transmission of the virus. So T is the probability that a contact between a susceptible and an infected person results in transmission. So we do C times T times S. That tells us the number of people that are that are newly infected each day, and then we multiply that by the duration of the infection, and that's really what R is. So the way to interpret R is that it's the average number of new infections created in a population by each person that is infected. So if R is bigger than 1, that means that each infected person is creating more infections in the population once they recover than the population started with. On the other hand, if R is less than 1, then each infected person leaves a smaller number of infections in the population once they've recovered. So just as a quick example, let's suppose that we look at these two infected people that we have in the population. And let's suppose that R is equal to 2. Well, what that means is that the person on the left is going to infect these two people in the population. So this person on the left is going to recover. These two people will become infected. This person on the right is currently infected. They're going to infect these two people. And what we're left with then is 4 people infected in the next period. So R is bigger than 1, so our number of infections tomorrow is bigger than it was today. On the other hand, if R is less than 1, in this case R is equal to 1/2, then let's suppose we have 2 people that are currently infected. They are each going to infect 1/2 of a person on average, so that means if we have 2 infected people, we're going to go to just 1 infected person in the next period. So our epidemic has gotten smaller. The number of infected people tomorrow is less than the current number of infected people today. So here's our 1 person coming from the 2 previous infections. Now, what is R for the coronavirus, and how does it compare to other infectious diseases? So this is some data from that's presented on Joseph Eisenberg's webpage. So he's the chair of epidemiology at the School of Public Health at the University of Michigan. And what we see is for the current coronavirus outbreak, we don't have precise estimates yet, but it's believed to be somewhere between about 1.5 and 4. Now, if we compare that to some other infectious diseases, we can see that our usual seasonal influenza, the reproduction number, or R, is typically between 2 and 3. The H1N1 influenza epidemic had a reproduction number a little bit less than 1.5. And interestingly, one of the infectious diseases that has a really, really big reproduction number is measles. It has, again, a reproduction number R, estimated to be somewhere between 12 and 18. So measles is really, really infective. It's easy to go from 1 person to many people very quickly with measles. But the important part of the coronavirus outbreak is that the reproduction number is at least in the ballpark of being pretty similar to seasonal influenza. Now, small differences in the reproduction number can, of course, have a big impact on how quickly an epidemic grows, because, as we'll see in a little bit, epidemics grow exponentially. So a small change in R can have a big effect on how quickly an epidemic grows, but at least in ballpark terms, it seems to be pretty close to seasonal influenza. Now, one thing to emphasize here is that R depends on S, the fraction of susceptible people in the population. And this will tell us kind of why we get that typical shape that we see out of our SIR model. So what I want you to think about is, as an epidemic grows, we have to have people moving from state S into state R. So if people are leaving state S and moving into state R, then the number of susceptible people in the population has to be getting smaller unless we're somehow replenishing those susceptible people. Right? And in the long term, we do, right? We have new people being born into the population, but if we think about the scale of time, the growth of the coronavirus outbreak is much greater than the number of new people that are being born into the population. So as it spreads, S is getting smaller. And remember that as S gets smaller, because we're multiplying C times D times T times S here, then the reproduction number must be getting smaller. So what this means is that as the epidemic grows, S gets smaller, this reproduction number eventually is going to be less than 1. What this means is that the epidemic will eventually burn out. So the analogy that I like to use when I talk about this in the classroom is that S is kind of like the amount of wood that you have on a campfire. If you want to keep your campfire going, what you have to do is put more wood on the fire. But if we don't add more wood, then the fire is eventually going to burn out. And the same thing happens with these SIR-style epidemics. We'll burn through the susceptible population, and then the epidemic will get smaller. So we can bring back the spreadsheet that we used in the last lecture. And again, what you can see is we've got the epidemic, this red curve, sort of sitting flat underneath this green curve for a little bit. It eventually starts to increase, we hit the peak, and then it dies out. And note what's happening to the blue curve. So the blue curve is the number of susceptible people in the population. So as the epidemic takes off, we're moving people from state S into state R. So the number of susceptible people in the population is getting smaller and smaller and smaller. As that gets smaller, we know our reproduction number is getting smaller. And at exactly the point where S gets small enough that R drops below 1, that's exactly at the peak of the epidemic. So as soon as S gets small enough that we hit the peak, then what happens is the epidemic starts to decrease and it eventually dies out and the number of new infections stops. So a last note on this reproduction number. One thing to keep in mind is, particularly with a new virus like the novel coronavirus that's currently spreading, is that early in the epidemic we expect S to be pretty close to 1. We expect most of the people in the population to be in the susceptible population because we don't have experience with it. It doesn't appear that we have some natural immunity to it either. So if S is pretty close to 1, then what we can think about is that this reproduction number, at least early in the epidemic, is pretty close to just C times D times T multiplied by S, but S is really just 1, so we can write the reproduction number for early in the epidemic as just C times T times D. And this is kind of a special number that we talk about in epidemiology, and we refer to it as either R0 or R0. And you can think about this as the reproduction number that you have at the beginning of an epidemic. And we'll use this R0 a little bit later in one of the following lectures. So the next thing that we're going to do is we're going to talk about this concept of herd immunity, which is something you might have heard about. We're going to talk about how it depends on the reproduction number, and specifically how it depends on R0 or R0. And then we're going to talk about how we can use vaccines to create herd immunity. So that will be part 3 of the lecture series on the coronavirus outbreak.